I want to introduce tonight's speaker, Louis F. Geschwinder, PE, PhD. Dr. Geschwinder is a former Vice President of Engineering and Research at AISC. He's Professor Emeritus of Architectural Engineering at Penn State University and Senior Consultant at Providence Engineering Corporation. He received his bachelor's degree in building science from Rensselaer Polytechnic Institute and both his master's and PhD from Penn State. He is a registered professional engineer and taught at Penn State for more than 40 years. Dr. Geschwinder is currently a member of the AISC Committee on Specifications and chairs the Member Design Technical Committee. Dr. Geschwinder has been the author and presenter of many presentations on behalf of AISC, and in fact, in recognition of his commitment to quality education and structural steel design, the AISC Seminar Series has been renamed in his honor. Lou, welcome. Thanks for being here, and I will hand things over to you.
Thank you, Brent. Appreciate that, and welcome, everybody. As Brent said, this is basic steel design, and I want to emphasize that this is a review of the principles of steel design, and it's according to the current version of the AISC 360 spec. So hopefully you've all had basic steel design, and this is going to bring you up to speed. This is not for someone who doesn't know anything about steel design. So we're going to have an introduction, review of basic principles. As I said, it's well suited for someone who may not have designed in structural steel for some time, but still has some experience. It's also going to be useful for those who think, you really need to review to improve your capabilities, and particularly in these areas that we're going to touch on today, maybe you need to be updated to the new specification. But we're not going to be saying, all right, this is new for this year and different than this from last year. We're just going to be concentrating on the 2016 specification. So let's look at tonight, this introduction. What are we going to see tonight? We're going to start by talking about the AISC specifications and the manuals, where this all started. Then we'll talk about structural safety. We're going to talk about this very important concept called the design basis. This is what allows us to put this whole specification together the way that we do, and it's important that we understand this. Then we'll look at the shapes of structural steel that are available to you as a designer. We'll look at the materials that are available to you, and then we'll end with a little bit of a touch on structural analysis. Now, in the early days of steel construction, we didn't have structural engineers going around doing all this. Architects were generally trained to do whatever needed to be done. There were no standardized specifications for steel. In fact, cities may have had their own specification. There were privately published specifications in textbooks, and there were standards that were published by the producers. So you can imagine the difficulty in doing a design in steel back in the early days, in the late 1800s. You had to know what city it was in. You had to know who was providing the steel in order to come up with a design. Back in that time, there were steel buildings being built. So the Home Insurance Building is considered the first skyscraper, built in 1884. It's at 135 South LaSalle Street in Chicago, designed by William LeBaron Jenney. Originally 10 stories tall. Later, it was added to. It was torn down in 1929. Now, the interesting thing is that this building started out, it was not steel. It was iron. Partway through the construction, steel became available. And so the producers asked if they could substitute steel for the cast iron that was being used. And they were given permission, so this became the first steel skyscraper. Next one to look at here is the Rookery. Again, Chicago, 1885 to 1888, designed by Burnham and Root. It's the oldest standing high-rise in Chicago. It's bearing walls on the outside and a skeletal frame inside. Then the Tacoma Building, 1887 to 1889 by Halliburton Roach, considered to be the second skyscraper. In this case, we have cast iron columns and steel beams. And this was the first use of all riveted connections. In this case, it really is a true skyscraper in that the steel frame is up and the brickwork is just hanging on. And in fact, the brickwork was started simultaneously at different levels in the building. So it was absolutely clear to anyone who walked by that the brickwork was not self-supporting, because there's brick up in the sky that wasn't supported on anything but the steel and cast iron that it was attached to. Then we get to the Rand-McNally Building, 1888 to 1890 by Burnham and Root. And this is the first all-steel skyscraper, columns and beams, 10 stories. And it's interesting to me that it's very difficult to find a photograph of this building. This is one of the few photographs that are available on the Rand-McNally Building, even though it is the first all-steel skyscraper. Then the Reliance Building, built in two parts, the base in 1890 and the upper stories 1894 to 1895. And this is the first introduction of the Chicago-style windows, the glass exterior. The Leiter Building No. 2, 1891, it's the oldest surviving department store building. It's not a department store, but it's the oldest surviving department store building in Chicago. Keep in mind, those were all done before AISC, because AISC wasn't formed until 1921. The first priorities of AISC to provide industry standard shapes, industry standard design specification, and a standard of practice that could be used across all designs for steel construction. So AISC came into an environment where all of those buildings had already been built, but they recognized the need for standardization. The first specification approved by AISC was approved in 1923. By 1924, it had been adopted in 25 cities. Its primary objective, to promote uniform practice so that the designer could design no matter where, no matter who was providing the steel, they could design the same way. In October of 1924, Herbert Hoover, who at the time was Secretary of the Department of Commerce, sent a message to AISC saying, "It gives me pleasure to congratulate you and the members of the American Institute of Steel Construction on your splendid progress in simplification and standardization of your products and practices." 1 year, and they're being recognized as having had a significant impact on this goal of standardization. So in 1927, they published the first steel construction manual. This is then the predecessor to the steel construction manual that everybody is familiar with. 2016, the AISC specification was published. It is now referenced as ANSI, American National Standards Institute /AISC 360-16, the specification for structural steel buildings. July 7th, 2016, and you'll note it says AISC is committed to one steel building design specification. So this is what we're basing the course on. This is what design today should be based on. The 2016 specification on the left, which is the basic requirements. The 2016 seismic provisions in the middle, that's AISC 341. And the Code of Standard Practice, the contractual provisions on the right. So this sets the package for design of steel building structures. And along with that, we have the Steel Construction Manual, the 15th edition. Now, the manual includes AISC 360-16, the basic requirements from the previous slide. and it includes the Code of Standard Practice, the contractual provisions from the previous slide. If you're interested in the seismic provisions, there is a seismic design manual, and that's where you're going to find that. But that's not what we're going to be talking about throughout this entire course. So the 2016 specification, let's take a look at that. We'll start with the mission statement of the committee. The mission was to develop the practice-oriented specification for structural steel buildings that provides for life safety, economical building systems, predictable behavior and response, and efficient use. This is essentially the same mission statement that AISC has had all along. It wasn't exactly written that way, but that is essentially what the goal has been. So let's look at the table of contents of the specification. We'll do that, and then later on we'll look at the table of contents of the manual. But the specification starts out with the list of symbols, followed by the glossary terms, and then abbreviations. And then we get into the chapters in the specification. So Chapter A are the general provisions. Chapter B are the design requirements. Chapter C is design for stability. And then we get the member design chapters. Chapter D, design of members for tension. Chapter E, compression. F, flexure. G, shear. And then Chapter H, design of members for combined forces and torsion. Brent mentioned that I think that I chair one of the task committees of the specification committee, and Brent is the secretary of that committee, and we are responsible for chapters D through H. So all of the member design is the responsibility of our task committee. Then we move to another task committee responsible for Chapter I, which is design of composite members. And then we get to connections. So J and K are the responsibility of another committee. Chapter J, design of connections, and Chapter K, additional requirements for HSS and box section connections. Then we have Chapter L, design for serviceability, Chapter M, fabrication and erection, and Chapter N, quality control and quality assurance. That's followed by 8 appendices. Appendix 1, designed by advanced analysis. Appendix 2, designed for ponding. Appendix 3, fatigue. Appendix 4, fire. Appendix 5, existing structures. Appendix 6, member stability bracing. 7, alternative methods of design for stability. And when we get to our stability discussion later on, we'll see that Chapter C will reference Appendix 7 and Appendix 8, which is approximate second-order analysis. Now, these appendices are an integral part of the specification, so if you need to use some of them, they are mandatory. It's just that you may not always need to use them. Now we move to the Steel Construction Manual, 15th edition, Part 1, Dimensions and Properties. Part 2, General Design Considerations. Part 3, Flexural Members. Part 4, Compression Members. Part 5, Tension Members. Part 6, Members subject to combined forces. Then we get to Connections. Part 7, Design Considerations for bolts. 8 is welds. 9 are connecting elements, so those are the basics, and then the specific types of connections. So Part 10 are shear connections, Part 11 partially restrained moment connections, Part 12 fully restrained moment connections, Part 13 bracing and truss connections, Part 14 bearing plates, base plates, anchor rods, and column splices, Part 15, hanger connections, bracket plates, and crane rail connections. Now, in the 8 sessions in this course, we are not going to be touching on connections. Then we get to Part 16 of the manual, and this is critical because Part 16 is where we have the specification and the Code of Standard Practice and the bolt spec. This is where we have the legal aspects. of the specification. The manual is a handbook. It's a manual. It helps. It supports. But it is not the legal document. Then Part 17, miscellaneous data and mathematical information, kind of the things you can't find anywhere else. So let's talk about structural safety. The basic equation for design: required strength less than or equal to available strength. Now, if we admit that you might be designing in some material other than steel, I'm not sure why you would want to do that, but just assume that you're designing in some other material, you're still going to follow that same equation. Everything you have done as a structural engineer has been following that equation. The required strength had better be less than the available strength. So as we talk about the different design approaches, keep that in mind. No matter what you do, required strength less than or equal to available strength. Well, what is required strength? That's what we get when we do a structural analysis, right? We put loads on a model and we do an analysis and we get an answer, like maybe the moment on a simple beam. That is the required strength. It's also called the load effect. What is the effect of the load on the structure? That's required strength. Available strength is what you get from the specification. So if you look in the AISC specification, you're going to find all sorts of equations. And those equations will give you something like the nominal moment strength or the nominal shear strength. The specification gives you the strength based on limit states, modes of failure. Okay? That's how the whole specification is set up, defining ways that that element might perform, might behave, and then picking the controlling ones. So available strength is also called resistance. So required strength less than or equal to available strength, or load effect less than or equal to resistance. Sometimes you'll see it in an equation form like this. It looks kind of daunting. It's really quite simple. What we have on the left is the summation of all of the loads, Q, times an appropriate load combination factor, or load factor. And we just add them all up. That is the load effect. On the right-hand side, we have the nominal strength, R sub n, times, in this case, a resistance factor. So we have load effect less than or equal to resistance. The load effect is the way we measure shear, force. This is addressed primarily in Chapter C of the specification, where it tells us what we have to do in our analysis to be sure that we get the full load effect. Now, what are the things that influence that load effect? Well, first is the easy part, type of load, right? Live load, dead load, wind load, snow load. Those are the load effects based on the environmental or the use activities. Now, those load effects, those loads are going to vary. So live load won't be the full maximum live load all the time. I'm sitting in an office here, and there's hardly anybody. There's nobody here but me. So the load on the floor in this office is pretty low compared to what it would be when everybody is here. And you may be in those same situations. Another factor that influences the load effect is how we go about calculating it. Now, we all know that on a simple beam with a uniform load, moment is equal to WL squared over 8. But there are all sorts of ways to calculate the moment or the shear or the force, and we may do a better job sometimes than others. And so there's a variability in that. And then we've got the likelihood of all the loads occurring at the same time. So if you look at a particular building and you think about one in the northeast or further north, what is the likelihood that all the live load and all the dead load are going to be on that building. At the same time, you get the maximum snow load, and oh, by the way, the wind is blowing at its maximum amount. The likelihood of all the loads occurring at the same time is rather slim, and so we end up with load combinations. Those are factors that affect the load. Now, because of that variability, we can plot something called a frequency distribution curve, or a probability density function. So across the bottom, we have load effect. So right there at that particular point, we might measure the load in the building, and we would come in and measure the load at whatever this magnitude is, and we would find out of all the times we measured it, we got this number of measurements. We might also measure at some point way out here, and we only get this number of measurements. So you see, we're talking about frequency. All right, that's what we're talking about, how many times we measure that magnitude of load. We're assuming that it is a normal distribution, so that's the typical bell-shaped curve, and that's what my students always wanted to know. Did I curve their grades? They didn't really want a bell-shaped curve. They wanted one that had a peak at A's, I think. But that's the frequency distribution. The way we measure the ability of the structure to carry the load, considering the influence of each limit state. Now, when the structure or the element becomes unfit for its intended purpose, it's reached or exceeded a limit state. Okay, so we're looking at how does the structure respond to a particular limit state, a mode of failure. If it exceeds that, it has failed. Well, there's variability in that also. The material properties vary. We know that if we get a piece of A992 steel, sometimes it has a yield stress of 60, sometimes it has a yield stress of 50, sometimes it has another yield stress. It varies. But it meets the criteria set in the appropriate standard. If we take the dimensions of a piece of steel, sometimes it's a little bit bigger than it says, sometimes it's a little bit smaller. There's variability. When we develop a mathematical model for our structure, sometimes there's errors in that. When we assume we have a simple beam, but then we make a connection at the end of the beam that induces a little bit of moment restraint, then it's not a simple beam, so there's model error. Another point of variability is how the risk might increase if you have a failure type that is sudden. So if all of a sudden it falls down and there's no warning, that may be a problem. So that's going to have to be brought into consideration. We look at how important the member is in the system. The first story column on a 10-story building is much more important than one short infill beam on the roof. And then we've got how familiar is the designer with the method that they're using. If the designer is not at all familiar with it, that influences also the resistance. So we get a variability of resistance, and again, we assume a normal distribution. Now, the goal here, remember, is that the resistance is greater than the load effect. And so if we superimpose the resistance curve and the load effect curve, we see that the mean value of the curve, all right, the mean value, let me get that pointer back here. right there. The mean value of the resistance is greater than the mean value of the required strength or the load effect. The problem is we have these points where the curves overlap. So let's take a look at data set 1. All right, data set 1 are the yellow points right there and right there. The resistance is down here. The load effect is up there. That means failure. The load effect is higher than the resistance. If we look at data set 2, the resistance is there, the load effect is there. Again, failure. The load effect is greater than the resistance. But if we look at data set 3, we see that the load effect is here, the resistance is there. Resistance is greater than load effect, so that is an acceptable situation. All right, so just because you fall in that region that I've labeled as failure does not mean that there is actually a failure in the structure. It may fail, it may not fail, it depends. And so we're going to take another look at this in a little different way. We're going to subtract the load effect from the resistance. So if we do that, then anything 0 or below is failure. Anything above is acceptable. Now, this is not just plotting the difference of those two previous curves. What we have to do is take the difference of these data points and then we find a new mean. But what this figure introduces is a new term, the beta term. Okay? The beta term right here is what's called the reliability index. And that is a multiplier times sigma, and sigma is the standard deviation. So now we can begin to see how to make this structure safer and safer by pushing the mean to the right. But rather than do it with just the resistance minus the load effect, it's actually done with the log, the natural log of the resistance divided by the load effect. And that allows a better statistical analysis of what's going on here. Now that, of course, is way beyond what we're going to be talking about. But when you do it in the log fashion, you end up with this area down here in red as the probability of failure. And we still have beta, the reliability index, and we want to push that mean as far to the right as we can in order to get a reasonable level of probability of failure. So, the beta index is how we measure safety. It's based on the number of standard deviations that the mean value is offset from 0. So if we're only offset from 0 by one standard deviation, we are covering 68% of the values. But if we push it to 2 standard deviations, we're covering 95% of the values. So what that means is if we're here at 2 standard deviations, from here to a symmetric point over here, this is the region that covers 95% of the values. And then over here at the right-hand end and over here at the left, which is already red, Together they cover 5%, which means we only get 2.5% of the values falling in the failure region. And what that ends up meaning is when we go to 3 standard deviations, the probability of failure is 1.4 times 10 to the minus 3. All right, that is the likelihood of failure defined by that curve if we use beta equals 3, which is what is used in the statistical development of the AISC specification. We don't often talk about the fact that there is always a probability of failure. We like to think of our structures as always being perfectly safe. But remember that that probability of failure includes things like what happens if the load is higher than the design load. All right, so if we design for 3 foot of snow and we get 10 foot of snow, we may have to shovel the roof. But the probability of failure is deemed to be so small as to be something that we do not need to worry about. And that's the responsibility of the specification committee. They're the ones that set beta equals 3. All right, let's look at the other side of that same equation now. Let's talk a little bit more about resistance. All right, so the resistance is based on the strength limit states, and that's the majority of what the AISC specification deals with. But we also have limit states associated with serviceability, beam deflection, drift, those kinds of things. That really is what controls in steel design quite often. But the specification, the manual, most of our academic courses spend the majority of their time on the strength limit states. But the design engineer is going to deal with the serviceability limit states also. When we talk about the strength limit states, there are basically 3: yielding, buckling, and rupture. Now there are some others, and each of those yielding, buckling, and rupture limit states often end up with a modifier. And as we go through the course, I want you to keep in mind there are those 3, but you'll find many of them modified. So we're going to talk about local buckling or tension rupture. So when we do that, remember that's one of the 3 basic ones. This is what's addressed in chapters D through K of the specification. The serviceability limit states are addressed in chapter L of the specification. Deflections, drift, vibration, wind-induced moment, thermal expansion and contraction, and connection slip. These are all serviceability limit states. Generally speaking, the specification is not going to give you much information on these. It's going to tell you, well, you better consider them, you better think about them, but it's not going to tell you, well, limit your deflection to 1/360th of the span for the live load. Now, the available resistance is determined by taking the nominal resistance, the equations we have in the specification, and multiplying them by a resistance factor. Now, what I am talking about when I talk about resistance factors is load and resistance factor design. You should all remember that if you've all designed in steel. We'll get to allowable stress design or allowable strength design later. Now, the nominal resistance is determined through an equation in the spec, and I'm giving you one example here. The nominal resistance or the nominal strength for a tension member that's going to yield is simply the gross area, A sub G, times the yield stress. That's very simple. The resistance factor is established through a statistical analysis looking at the variability of all of the things associated with the load effect and all of the things associated with the resistance calculated by that equation. A statistical analysis is conducted and a resistance factor phi is determined. when we look at the things that influence the variability of the resistance equation, we have these three factors: modeling, material, and fabrication. So modeling is, I predict the plastic moment of my beam is Z times the yield stress. And then I conduct a test and I get a plastic moment. The ratio of the plastic moment I get in the test and what I predicted by my equation is my modeling. We specify A992 steel has a yield stress of 50, but when we actually take a specimen and test it, we find it has a different yield stress. That's going to enter into the material variability. And when we talk about fabrication, what we're talking about are things like, what is the plastic section modulus given in the manual, and what is the actual plastic section modulus if I measure very carefully every piece of that section. So that's the fabrication variability. All of those are going to influence the variability of the member. Now, the typical resistance factors that come from that analysis for yielding limit states, we use a phi of 0.9. For rupture, we use 0.75. And I said there were others: connection slip, phi of 0.7, composite components with shear studs, a phi of 0.65. So you will see a variety of those. And from those, we will end up with safety factors if you want to do ASD design. And we'll see how we do that in a little bit. The load effect variability is given by this kind of an equation, and we're not going to have to use this, but if we simply take this equation, the D is dead load, the L is live load, the A and B are the uncertainties associated with taking that live load and that dead load and transforming it into a load effect. The CD and the CL are influence coefficients having to do with, if I put a load here, how much of that load actually influences the other member over there. And E represents the uncertainties in our structural analysis. From all of that, we will figure out a load effect. Now, if we look at AISC E7 for the loads, these are all things we know. L is live load, L sub R is roof live load, W is wind, D is dead, S is snow, E is earthquake. These are the loads. AISC E7 committee has looked at the variability of those loads, and they have come up with the AISC E7-16 load combinations. And I'm giving you just some examples here. These are the ASD load combination, just some of them, and these are the LRFD load. These are the basic load combinations. If you're actually going to do a design, you want to go into AISC E7 and make sure you know what is going on there. Now let's see about comparing ASD and LRFD and looking at things called load factors. In 1986, LRFD specification was calibrated to the current ASD specification. The situation was there really wasn't anything wrong with design according to the ASD specifications. Steel buildings were not falling down all over the place. They were perfectly fine. They were not overly conservative in their design. They were pretty good. And so the committee that developed the LRFD specification decided that they would calibrate the new LRFD specification to the old ASD specification at a live to dead load ratio of 3. Now, you know better than I how often in the designs that you do on a regular basis, your live to dead load ratio is 3. Sometimes it's more, sometimes it's less. Any time that you have any load other than live and dead, you get a different relationship. This does not hold. So this only holds if you have live load and dead load. Now, the LRFD load combination for dead load and live load is 1.2 dead plus 1.6 live. The AISD load combination is just dead plus live. And so what we want to happen is a design by AISD and a design by LRFD give you the same answer at a live to dead load ratio of 3. So since AISD uses the same load factor on dead and live, we can write the AISD as gamma times dead plus live. And we can set that equal to the LRFD load combination, 1.2 dead plus 1.6 live. And then if we use a live to dead load ratio of 3, we find that the effective load factor is 1.5. So at a live to dead load ratio of 3, the effective load factor is 1.5. So this means that for AISD, we are effectively multiplying dead by 1.5 and live by 1.5, even though we don't see it in the actual design. It enters through the safety factor. If we vary the live to dead load ratio, it doesn't change in AISD, but it does change in LRFD. And this is what it looks like. The green that you see is 1.5. That is the load factor, the effective load factor, regardless of the live to dead load ratio. But the blue is the LRFD load combination. And I snuck in this piece down here from 1.4 down to 1.24. That is the part that is due to the load combination 1.4 dead. That's when you have primarily dead load. The 1.2 dead plus 1.6 live is the rest of the curve, right? This part here all the way out to here. And I've only plotted it up to 12, but if you go all the way out to infinity, a live to dead load ratio of infinity, that means all live, no dead, you end up with a 1.6 load factor, which is 1.2 dead, which dead is 0, 1.2 dead plus 1.6 live. So you see that we get different effect in AISD and in LRFD. Now we can determine the safety factor. If they're equal, 1.2 dead plus 1.6 live has to be less than phi times r sub n, where phi times r sub n, this is the available strength using LRFD. For AISD, dead plus live has to be less than or equal to r sub n over omega. So what we're going to do is we're going to solve those two equations for the nominal resistance, R sub n. And then we're going to set them equal to each other, substitute live over dead equals 3, and solve for the relationship between phi and omega. And we see that omega, which is the safety factor that we're going to use in AISD, is equal to 1.5 divided by the resistance factor that we're going to use in LRFD. So there is a consistent, direct relationship between the resistance factor in LRFD and the safety factor in AISD. The interesting thing is that that is not the case on the load combination side. So if you were to go into the AISC E7 load combinations and figure out for some particular load combination, and it doesn't have to be just dead and live, it could be dead and live and snow, figure out the force in this member due to LRFD and the force in this member due to ASD load combinations, you would find that the relationship is not 1.5. It varies. It depends on the load combination. But when it comes to the strength side, the relationship between the ASD strength and the LRFD strength is always 1.5. Now, where do we get safety in all of this? Remember that our structures have to be safe, right? Required strength has to be less than or equal to available strength to have a safe structure. In ASD, safety is established through the safety factors, but also through the ASD load combinations. In LRFD, safety is established through the resistance factors, and again, the LRFD load combinations. All right, so we've got 2 points, whether it's ASD or LRFD, 2 points to influence the safety. Safety factors in load combinations or resistance factors in load combinations. Now, since we have that consistency on the strength side but not on the load side, what we're going to end up with is variability in the reliability index. And so if we look at reliability now, and this is for a compact laterally supported beam, and we're looking at different live to dead load ratios, you see that on the low live to dead load ratio, I plotted here a live to dead load ratio of 1. You see that the LRFD reliability is about 3. The ASD reliability is about 3.5, 3.4, something like that. If you go to the other end, and this is about 5.5 out here, you see the ASD reliability is 2.5. The LRFD reliability is, say, 2.6. All right? You do not always get the same level of reliability, and that is perfectly acceptable. That's what the specification committee is working with, and the committee has determined that this range of reliability is acceptable. Now, when you go and design a connection, what you'll find is the reliability index on a connection is going to be higher than this. Remember the sudden failure kinds of things, the importance kinds of things. These all come into play as we set the reliability index as we write the specification provisions. So we have different levels of reliability, we have different load combinations, we have different resistance and safety factors, but all of that is taken into consideration by the specification committee as they write the specification. And the level of safety is deemed acceptable by the committee as they look at the statistical basis. Now, these are important definitions. We've talked about them along the way, but I want to summarize them here. First is required strength. And if you see an equation in the specification where it talks about required strength, and it may be talking about an ASD or an LRFD, you're going to see R sub R. That's the required strength. If it's just talking about ASD, it would be R sub A. If it's just talking about LRFD, it would be R sub U. The nominal strength is R sub N, and it doesn't matter how you're doing your design. The nominal strength is the nominal strength. And then the available strength, again, if you're looking at available strength when it could be either ASD or LRFD, you're going to use R sub C. But if we're talking about ASD, it's allowable strength, and that is R sub N over omega, R sub N over the safety factor. And if we're talking about LRFD, it's design strength, and that is phi times R sub N. These terms have been used ever since the 2005 specification, 360.05. That's when the unified specification, bringing ASD and LRFD together in one specification, that's when that was formed. All right, so Chapter B, Section 3.1, the design basis, the foundation of all of the specification, says for LRFD, design shall be performed in accordance with required strength less than or equal to available strength, which is given by R sub U less than or equal to phi times R sub n. And the definitions are there for R sub U, R sub n, and phi. And B3.2, for ASD, design shall be performed in accordance with, again, R sub A less than or equal to R sub n over omega. And again, the terms defined, we've already talked about them. To look at some very simple applications, we'll look at tensile strength for the limit state of yielding. Remember, we said everything is going to be based on a particular set of limit states. So the limit state of yielding and tension is given by this equation, P sub n, the nominal strength is equal to Fy times A sub g. And right after that in the specification, it's going to tell you that phi is 0.9 for LRFD, and omega is 1.67 for ASD. So if we set that up, substitute that FYAG in for P sub n, you see P sub U, the required LRFD strength, less than or equal to phi times FYAG. If we do the same thing for ASD, P sub A less than or equal to FYAG over omega. That is how the entire specification is laid out. The design process is fairly straightforward. Determine the required strength after you've decided whether you're going to use ASD or LRFD load combinations out of the building code. Determine the required strength. Determine what are the limit states that I need to check. And the specification is going to tell you exactly what limit states you need to check. For each of those limit states, the specification is going to give you the equation, so you're going to determine the nominal strength for each of those limit states. Then you're going to determine the available strength for each of those limit states, and that means you're going to use the appropriate resistance factor or safety factor. And then you're going to confirm acceptability, and acceptability means required strength less than or equal to available strength. And in every situation, the levels of safety and reliability are as established by the specification. All right, so that's the introduction of the specification, the kinds of things you're going to see there. Now, we're going to go through the design of individual types of members, and we're going to see exactly how that applies. But for our introduction here, we're now going to look at the structural steel shapes that are available for us to use in our design. Now, the majority of the shapes that we use in design are defined by ASTM standard A6, and the standard that is used in the 15th edition manual is the 2014 standard. There has been a revision since then, but that's the one that is used in the 15th edition manual. And this is the standard specification for general requirements for rolled structural steel bars, plates, shapes, and sheet piling. So this is where we get the information on W shapes, S shapes, HP shapes, M shapes, C shapes, MC shapes, and L shapes, and bars and plates. We don't do anything with sheet piling, but the same information is there. There are other standards for other shapes, like the hollow structural sections, the hollow shapes. And there are several ASTM standards that define these shapes. ASTM A53, that is a standard that applies to steel pipes. Then there's A500, A501, A618, A847, A1065, and A1085. These standards deal with both material and shape. The A6 standard just addresses the shapes. It doesn't talk about the materials. But the hollow structural sections address the material as well as the shape. And these standards cover round tubing, square tubing, rectangular tubing, and steel pipe, which is like the round tubing, but it's made to the A53 standard instead of any of the others. So if we look through the 15th edition manual, and these are just the top half of each of these tables in the manual. So what we see is the W shapes, and the typical designation for a W shape is a W16 by 26, meaning that it is nominally 16 inches deep, and it weighs 26 pounds per foot. There are 283 different W shapes in this manual. Now, since there's a new A6, there may be more, there may be less in the next version of A6. Depending on which version of A6 is available when the 16th edition manual comes out, that number may change. But right now, that's the number published in the book. The M shapes, there are 18 of them. The S shapes, there are 28. The HP shapes, there are 22. Each of these shapes, the number following the shape designation, WMSHP, that next number is the nominal depth. And the last number is the weight in pounds per foot. And if you look at the figures on this slide, you will see the kind of shape. The W shape is a wide flange. It's very similar to the HP shape. The flange outside and inside are basically parallel. If you look down at the S shape, what you see is that the inside of the flange is tapered. It's sloping. That's an indication of an S shape. If we go on to the channels, you see we have C shapes and MC shapes, and they also have that sloping inside of the flange. We get to angles. Table 1-7, we have 137 different angles. And then we get to WTs. Well, WTs are often referred to as split Ts because all a WT is a W shape cut down the middle. So they have the same 283 W shapes and 283 WTs. MT is a split M, ST is a split S. Then we get to the HSS. These are covered in tables 1-11, 12, 13, and 14. So table 1-11 are rectangular HSS, and there are 281 of them. Now, the designation for HSS is a little bit different. It's HSS 20, which means the nominal depth is 20, by 4, which in this case means the width is 4, by 1/2, which is the thickness of the wall. And in HSS, all walls are the same thickness. Square HSS, HSS 5 by 5 by 1/2, same nomenclature as far as the definition. Round HSS, you'll see it's an HSS 7 by 0.500. So that is a 7-inch outside diameter circle with a 1/2 inch nominal wall thickness. When you get to pipe, all you get is a pipe, 12 standard or 12 extra strong. 12 being the diameter, the outside, or I guess it's the inside diameter really, and standard is a way of defining wall thickness. 281 rectangular HSS, 107 square, 128 round, and then 51 pipe. That's what you'll find in the manual. So a total of 1,452 shapes. You ought to be able to find one that meets your needs. But then there are other shapes. There are combined shapes. So what you're going to find are double angles are going to be in here. The maximum weight of any shape in the manual is 925 pounds per foot. You want to think real carefully before you specify that member. That is one whopping big member. It's only 36 inches deep, but it weighs 925 pounds per foot. The lightest weight one is a half-inch pipe that weighs 0.85 pounds per foot. Now, if you remember that steel weighs 490 pounds per cubic foot, 2 square feet of steel, 1 foot long, is 980 pounds. So that W36 by 925 is not quite 2 square feet of solid steel. You, of course, can make any combination that you want out of these shapes and plates and bars. Anything can be combined. It's up to the designer to make the efficient shape if you're going to make one, because there's a lot of cost associated with making a shape as opposed to using one of the rolled shapes. Now let's look at material. The approved materials are given in section A3.1A in the specification, and it identifies 21 different approved materials. Now what I'm showing you here is table 2-4, and this table lists what are called preferred or other applicable materials. So if you start at the top, you'll see carbon steel on the left, and then the first ASTM designation. All right, so we are right up here, right? ASTM A36, and you'll see it's listed for W, M, S, HP, C, MC, and L. But the black bars are under M, S, C, MC, and L. So by looking at this, it looks like if you're going to use a channel, you probably should be using A36 steel. I just learned the other day that higher grade 50 KSI steel is now being used for channels. So you need to check with your supplier if you want to use some of the higher strength materials. If we then look at way down here at the bottom, we see high strength, low alloy, A992 steel, and that is where you find the wide flange shapes. Okay? So if you're going to use a W shape, you're going to want to use A992 steel. For hot rolled structural shapes, there are 8 different materials specified. For hollow structural sections, there are 7. For plates, there are 10. For bars, there are 4. And for sheets, there are 2. So there is a wide variety available to you, but all of this gray area here, probably don't want to use that unless you've determined that it is readily available and that you have some good reason to want to use that material. All right, so the preferred material for wide flange shapes is A992, has a yield of 50 and an ultimate of 65. Already did the MSC, MC, and L, preferred A36. HPs, preferred A572 grade 50. For HSS, the preferred material is A500 grade C, and you'll see if you go back to that table that the yield and the ultimate will be different for rectangular versus round. And then if you happen to be using a pipe, which is A53 grade B, you'll see that the yield is only 35 KSI and the ultimate is 60. Now I've listed here the chemical components for A992 steel. All right? This is taken directly from ASTM A992 standard. And if you want to look at that, I would encourage you to find the standards that apply to the materials that you're working with so you have an idea of what's being specified. But if we quickly run through the materials, all right, carbon is the most common element after iron. Then comes manganese, then silicon, then vanadium. And if you look here, you'll see, all right, carbon increases strength, decreases ductility. Manganese improves notch toughness, but has negative impact on weldability, has similar impact on strength as carbon does. Silicon removes oxygen from the hot steel, so it has some value, but there may be other reasons. Vanadium increases strength, but does not negatively impact weldability. Columbium increases strength, but has significant negative impact on notch toughness. Phosphorus, sulfur, all of these things have potential positives and negatives. Copper, if you want corrosion-resistant steel, you're going to get a good bit of copper. Nickel improves notch toughness. Chromium, primarily for stainless steel. And molybdenum. Those are all the components that go into making steel, particularly A992 steel that I was showing you there. Now, if we look at steel as a material and go back to our basic mechanics classes, we remember the stress-strain curve for steel, and if we expand the horizontal axis quite a bit, we are reminded that in the beginning, it's a straight line stress-strain curve, not that I can draw one with this thing, but it's a straight line stress-strain curve up to a point we call the yield stress or the yield point, and then there is a horizontal plateau, which is defining plastic behavior, and then it reaches a point at which it goes into strain hardening before it reaches the peak, its ultimate strength. So F sub y is the yield stress down here. F sub u is the ultimate stress up there. The slope of the curve is the modulus. In the beginning, the straight line is the modulus of elasticity. This strain, E sub y is the yield strain that corresponds to the yield stress. Okay, so that's the material that we're working with. Now, if we expand that and look at some higher strength steels, what you see is the A36 steel is down here. It behaves very much like what I showed. Higher strength steel, like A992, is right here, and it still behaves pretty well the same way. But as we get up to higher strength steel, up to 100 KSI, you'll notice we don't have that same obvious flat plateau. There is continual increase. So the higher strength steels will behave a little bit different than the lower strength steels. If the AISC specification says it's okay to use this steel, then they have taken into account all of the considerations that you need to take into account as far as does it behave the way it should behave. Now, let's quickly look at the structural analysis. Here's a beam. It's got 4 kips per foot on a 20-foot span, simple beam moment, 200-foot kips. Here's a column. Has an axial load of 400 kips, load on the top 400, reaction on the bottom 400, force in the member 400. Very simple. You can all do that. But if we put these two things together, we will get something else. So what we have with the simple beam moment or the force in the column that we just did is called a first-order analysis. When we put them together, the fact that that uniform load causes this beam to deflect means that that axial force is going to add moment to that 200. That 200 foot kips, remember, is the simple beam moment. But this 400 kip force moving through this deflection means that there's more moment here than that 200. And that is coming from what is called a second order analysis. So we must account for that increase. AISC Specification Chapter C requires that we design for those second order effects. Now, some people might think that this is something new, but it's not. It's always been there. But more importantly, it's important for us to understand that that really is important. It really makes a difference. So I'm going to look at these three possibilities: a column, axial load, and equal bending moments at each end; a column, axial load, and uniform gravity, or in this case lateral load; and a flagpole column with a gravity load and a lateral load. So if we start with the uniform moment, 400 kip axial load, 200 foot kip moment, this happens to be a W12 by 96. If we calculate the deflection due to a uniform moment, 200 foot kips over the full length, the deflection at the middle, right here, 0.715 inches. That 400 kips times that 7.15 inches gives us a moment of 23.8 foot kips. We thought we had 200, but what we really have is 224. That is a 12% increase in the moment, an amplification factor of 12%. But that was just a first guess. If we go another step and say, well, let's assume that that 224 foot kip moment we have is also applied uniformly. All right, it's not really, but I'm going to assume that just to simplify it. Okay? There's the 23.8 additional moment. There's an additional 0.85 inch deflection. That gives us an additional 2.84 foot kip moment. So now our moment's 227 foot kips, which gives us an amplification factor of 1.14, 14% increase. Now, because of the simplification on the moment diagram that I made, this might be a little bit higher, but we know from our previous slide it's at least 12% increase, and so that 14% increase can't be too far off. If we look at the beam with an axial load, this gravity load, giving us a max moment in the middle of 200 foot kips, uniform load deflection 0.596 inches. That means the added moment is 19.9 foot kips. So our first shot at our second order moment is 220 foot kips, or a 10% increase. And then we take that 220 foot kips moment and put it here, and the moment diagram is pretty much going to look like the same shape as the moment diagram for the uniform load. It won't be exact, but it will be pretty close. So if we take that additional 19.9 foot kip moment, we get an additional deflection. That additional deflection gives us an additional moment. We add that, and you see now our amplification is 1.11. And that's going to be pretty close because the shape of our moment diagram was pretty close. Now, if we look at the flagpole, I've got a 10-kip horizontal force, which means the moment at the bottom down here, due to that 10-kip force, is, again, 200 foot kips. So, again, we've got a moment of 200 and an axial force of 400. So all three of these have the same axial force and the same moment. But now the deflection at the top is due to this horizontal force, so it's HL cubed over 3EI. we get a 1.91-inch deflection. That means down at the bottom, because that force moves over to here, right? Once it's deflected, the force is over there, and so the moment is that distance, 1.91 inches times the 400 kips. We're adding 63.7 foot-kips of moment. That 63.7 foot-kips added to the 200 is now 264, and now you see our first try, we've got a 32% increase, an amplification factor of 1.32. Well, I'm going to put that 264 foot-kip moment down here. I'm going to assume that it goes by that straight line, which isn't correct. It should go by the curve, so I'm underestimating it. But if I do that, I can take that 63.7 foot-kip moment and divide by 20. So what I really have is an additional 3.19 kip force up here at the top. Gives me an additional deflection of 0.608 inches, an additional moment of 20, and now my moment is 284 foot-kips, which is an amplification factor of 1.42. And this, we know, is going to underestimate because of the way we assumed that moment diagram. That is not insignificant. And since we know that underestimates it, we know it's going to be more. So we cannot ignore these second-order effects. It's critical that we address second-order effects. So my hope is, I don't expect you to have followed all those numbers as quick as I went through them, but I want you to get from that is that second-order effects are real. They can be very significant, and they are going to have an impact on your design. So for tonight, we looked at the basics. We looked at AISC as the basis for structural steel design. We looked at safety and a model for developing the specification, where the variabilities come from. We identified all of the possible shapes that you might have available to you. We reviewed basics of steel as a material, and we had a very quick look at structural analysis. Now, I hope between now and next Tuesday, you will go back and look at those slides, look at the steel manual, look at the specification, get a feel for the different parts of the specification, and try to get a handle on all of the resources that are available in the manual, and if you want to know more about the material, in the ASTM standards. Next week, we're going to look at the principles of design for tension members. So that means we're going to be primarily looking at Chapter D of the specification and Part 5 of the manual, because Part 5 of the manual are the tables available for tension members. So, Brent, that brings it to the end of my presentation. If you want to take over, we can...
Okay, thanks, Lou. Why don't you go ahead and stop sharing?
I am doing that.
Okay, thanks, Lou. All right, everyone, we've jumped back to the slides window, so hopefully you should see that adjust on your screen. If you were in full screen mode, you need to escape and choose that slides window for the remaining portion of tonight's presentation. Okay, we do have several questions from the audience, Lou, but before we do that, we're going to do a couple polling questions for our audience to make sure everyone is paying attention. So here is our first polling question. Select all of the following statements that were AISC's first priorities. A, develop an industry standard database, industry standard shape database. B, establish a standard design specification. C, ensure existence of an industry standard of practice. D, make steel the material of choice. E, compete with wood design. Again, you can select more than one answer, and we want to look for all of the following statements that were AISC's first priorities. You can simply click on the box next to the answers you think are correct on your screen, and then hit the blue Submit button, and we'll take a look at how the responses come out here in just a few seconds. Once again, you can select more than one answer.
They should select all that apply.
Okay, I'm going to give you about 5 more seconds, and then I'm going to close this up, and we'll take a look at the results. Okay, the polling is closed. Let's take a look at the answers. So Lou, it looks like the majority of the people said that answers A, B, and C all aligned with the first priorities for AISC.
And that is correct. That's how AISC started, and the make steel the material of choice was the last catchphrase that AISC used, and we never talked about competing with wood design, although as the wood people try to make wood frame buildings get taller and taller and taller, we may get to the point where AISC is trying to compete with the wood design people. But it's important to know, right, the standard shapes database, and back in the 20s, it was not a computer database, it was just a list. All right? That was published in the manual. The standard specification and the code of standard practice.
Okay. Thank you, Lou. Let's hustle through one more polling question here. Select all of the following that are considered strength limit states: yielding, buckling, rupture, deflection, drift. Again, select all the following that are considered strength limit states. Go ahead and click on the box that corresponds to the answers and hit the Submit button on your screen. All right, just a few more seconds and we'll close that up. Okay, let's take a look at the results, Lou.
Well, they did a pretty good job on that one, too. So yielding, buckling, and rupture are the strength limit states. Deflection and drift are serviceability limit states. And I want you to keep in mind that we're going to see a lot of modifiers to yielding, buckling, and rupture as we go through the rest of the course, because we're going to be looking at specifically how they apply to the individual elements, members that we're talking about.
Okay.
So they're a particularly smart group of students tonight.
All right, great. All right, let's try to get through a few of the questions from the audience before we wrap up tonight. The first question, I'm on slide 28 here, Lou, is a question about torsion. So the title of this chapter is Design of Members for Combined Forces and Torsion. Why is torsion mentioned specifically and not just assumed to be a combined force?
Oh, I don't know. Probably because it doesn't occur all the time. We're not always dealing with designing for torsion. The section in Chapter H is called Members Subject to Torsion and Combined Torsion, Flexure, Shear, and/or Axial Force. That's Section H3. H3.1 is round and rectangular HSS subject to torsion. H3.2 is HSS subject to combined torsion, shear, flexure, and axial force. And then H3.3 is non-HSS members subject to torsion and combined stress. The thing about Chapter H and torsion is that it doesn't give you a whole lot. It's basically superimposing stresses. And you really are going to need to look at design guide, I can't remember the number, but the design guide on torsion to get a little more direction. I suppose, you could leave torsion out of there in the title, but since it is specific in some of the sections, the committee decided to add torsion to that title.
Okay. We have several questions on the various shapes that you hit on. I'll take us first to, let me get up there. Why can't I find it? There we go. The first question is, are shapes supposed to always be available commercially if they're listed?
No. No, there's nothing in ASTM A6 of any year that says that you can buy that shape. The producers can produce whatever they want. AISC has a resource on its website that will allow you to check to see who's got what kinds of shapes. There are some shapes that are in some materials are only produced offshore. There are probably shapes that are never produced. But AISC doesn't have anything to do with it, okay? This is an ASTM committee. AISC has, I think, one representative on that committee. The mills have representatives on that committee. There are other interested parties have representatives on that committee, and that committee decides what shapes may be produced to meet this standard. All AISC is doing is taking those shapes and expanding on them, because all of the information that's in the manual on those shapes is not in ASTM A6. So again, I encourage you to go look at what's in A6 and what shows up in the manual, because AISC has to do a lot of calculating to actually come up with like the section modulus and the area and the moment of inertia, those kinds of things.
Okay. Can you briefly tell us the difference between a C shape and an MC shape?
No. They're categorized differently for some reason. If you look in the manual, what's that, table 5 and 6? The way MC shapes are defined is there anything that doesn't fit in the C shape, which I always found to be an interesting way to define things.
Okay, and you're referencing table 1-5 and 1-6.
Yeah, table 1-5 and table 1-6.
Okay. All right. Let's hit on one more question before we wrap up. Someone asked about table 6-2, which looks at combined forces, and the question is, does table 6-2 take into account second order effects?
No. None of the tables in the manual take into account second order effects. Second order effects come from the analysis. All the tables in the manual give you is available strength. Right? So second order analysis is on the load effect side, required strength. The manual is on the resistance side, available strength.
Okay. All right. Well, thank you very much.